Welcome to a lesson with Dr. Powell. In this video, we're going to practice using properties of definite integrals, specifically even, odd, and also working with bounds. In this particular example, we will be trying to compute this definite integral from -2 to -11 of a function f of x, which is given to be odd. We are given some information of how this function integrates over two different intervals. Now, what does it mean to be an odd function in terms of integrals? So if you have an interval, this is 0 right here, and you have another interval symmetrically on the other side, so this is like a to b, and this is negative b, negative a. See how it's symmetric across? If we're integrating across right here and across right here, notice the direction going toward the positive, in the positive x direction. The integral from a to b and the integral from negative b to negative a, these are going to be negatives of each other. But you could also think vice versa. You could also say, this is another way of thinking about it. You could simply say that the integral from, if we did an integral in this direction, so if we're going from negative a to negative b, these are actually going to be equal. So if we have an odd function, so as we integrate away from, away and over here or in that direction, then these integrals will be equal. I mean, let's think intuitively of an example. Just a second, something odd symmetry. So if you reflect this way, then reflect that, and then reflect that way, so horizontally, then vertically, you'd end up getting the same, you end up staying on the same graph. So, and let's suppose this is 0, so that, and that's what we need if it's odd symmetry that way. So, and if we had that, thinking about if we integrate, this area is going to be the same as the backwards area going this way underneath. Notice going backwards and being below the axis are like two negatives that cancel each other out to make a positive. So really, this is the positive version of the area if we go integrate backwards, which is the same as this positive version integrating this way. Integrating backwards provides a negative, but then being below the axis provides another negative, so they would be equal. Okay, so that's how we can think about odd functions with integration. And okay, so as we go forward and think about what's happening here, notice we have 2, 7, -7, -11. So, and be thinking about symmetries here. So it looks like, there's a 7 and a -7. Maybe we can just kind of plot those things here. -7 and a +7, symmetric about 0. Also notice a -2 and 2. This is a -2 and a 2. And we have a -11 out here. Now, all right, we're given that the integral from 2 to 7 right here, this is -2 going in this direction. So what does that mean about from -7 to -2? That would mean that would be +2, just like we were describing if we're going in this direction. Now, however, if we want to go in the opposite direction, we could think about this as being going this way, as simply being -2, kind of symmetric this way and that way because it's odd. Okay, and we know that because we're given this -2 right here. for starters. And then using the symmetry, we know that this would be -2 going this way. Notice that we actually want the backwards. We're looking for the backwards integral from -2. This is what we're after, -2 all the way to -11. That's what we want. Now also notice that we actually know what this integral is. Excuse me. And this is given to us. Going from -7 to -11 is given to us as 3. So put this together, you add this integral to that integral to get the full integral from -2 to -11, which would give you a 1. So this definite integral would be equal to 1. Okay, let's look at another example. And this time, f is again odd, but we're dealing with two different functions, and integrals over, if you're adding two different functions, the integral actually splits. So you can actually think of this as being the integral of f of x from 4 to 7 plus the integral from 4 to 7 of g of x dx. Okay, so if we're going from, let's see what kind of information we have here. Well, first of all, we're in a lot of luck for g, because we're already given the information that g of x, the backwards integral from 7 to 4 is -10. So the forwards integral from 4 to 7 must be +10 for g. Now what about for f? Okay, let's see. We're going 4 to 7, but we're given information from -4 all the way to 7. But luckily enough, we actually know something. The full integral from -4 to +4, since f is odd of f, okay, is going to, this part's actually going to be 0. Notice this interval is symmetric about 0, and if you're thinking of an odd function, like our little picture, what, positive area and negative area, because we're always going in one direction, right? So right here will be negative, there will be positive, and it'll cancel out to 0. In fact, that's a nice application for odd functions. There are parts which will completely cancel out if they're symmetric about 0. If you have an interval, that part of the interval is negligible. Specifically, whatever this integral is, this part is the negative of it, so, and it's right back to back across, so they'll cancel out. So from -4 to 4, we know that's 0, but we're also given to know that from -4 all the way to 7 is 2, which must mean, since these things add together, that this length, the integral from here to here, must be 2. So, hey, that's 4 to 7. We're done, right? So really, we know we're going to have a 2 coming from here, and then a 10 coming from here. Added together will give us 12. And let's look at one last example here. This time, let's think about even symmetry. Now, what does even mean in terms of integration? Well, for an even function, it's symmetric about the y-axis. Think of this dotted line as the y-axis. So, and I guess I drew a x-axis there. I guess I didn't quite need that. But basically, across the y-axis, you're going to have whatever the function is here, it's going to be over there. And if you're integrating, let's think. If the x-axis is right here, then is not this area going in this direction positively the exact same as this area? I mean, the graph itself is just reflected, but it's reflected this way, and the area under the curve to the x-axis is going to be the exact same, even with the reflection, for an even function as we're going across. So really, if we know what the integral is right here, then the integral from here to here is just double. It's double what it was here. So this doubling effect is a nice idea for integrating even functions. In this particular example, we're looking for the integral of the even function f from 3 to 7. And we're given some information. Let's kind of think about symmetries for a minute from what we have. Notice that we have an interval from 3 to 7, but we also have a negative 3, and that's going to be symmetric about 0. Let's see, negative 3, 3, symmetric about 0, and off here we have a 7. Okay, now we know what the integral from negative 3 to 7 is. Negative 3 all the way to 7. That's going to be 4. So, and we also know that the integral from negative 3 to 0 is, in this case, also 4. All right. Now, since f is even, we know that if we go from 0 to 3 like this, it'll be the exact same thing again. It'll be 4 again. So the question is, what does it have to be right here so that totally from negative 3 to 7, it's going to be 4? Well, notice we have 4 plus 4, so 8, but we're going to have to subtract a 4 here to get back to 4. All right. Essentially, since this is 4 right here, the rest of the way has to be a 0. And since this is 4, we have to have a negative 4 right here. So it looks like this integral is negative 4. All right. And that concludes this little video. Thanks for watching.